Hello everyone. We have discussed LBJ algorithm for designing codebook in last videos, right? In this video we will discuss tree-structured vector quantizer. Its a short form is TSVQ. So in this video we will discuss what is tree-structured vector quantizers and how it is useful. This tree-structured vector quantizer technique is another fast codebook design technique presented by Buzo. It is presented by Buzo. In designing codebook with the LBG or k-means algorithm, we have assumed that for each training vector, we are testing the minimum distortion condition with each code vector. This method is called full search. So, this full search algorithm have high computational complexity. Why? Because you are computing distortion between each training vector and each code vector. Now, the number of operations can be reduced by enforcing certain structure on the codebook. If you enforce some structure on the codebook, then the number of operations can be reduced. One such possibility is using tree structure for the codebook. You will design codebook using some tree structure so that the number of operations is reduced. And this method, so the codebook will have tree structure and the method is called binary search clustering. Now assume L as a number of code vectors and L is a power of 2 here. L is a number of code vectors and it is power of 2 means number of code vectors is a power of 2. Here L indicates number of code vectors that you require in your code book. Now here the k-means algorithm is used for designing code book. What is k-means algorithm? In k-means algorithm you have some training set or training vectors and for the input data and you are representing this training set using some representative vectors. So you are selecting some representative vectors from the training set to represent all the training set. After selecting the representative vectors or code vectors, you are dividing the training data or training set into number of clusters, right? After dividing the training set into number of clusters, you are computing centroid of the cluster. Okay, centroid for the each cluster. How will you compute centroid of the cluster? Using mean value or using average value of all the training vectors present in that particular cluster. So this centroid will serve as a new code vector for that particular cluster. So this way you are computing the code vectors in k-means method, right? So by using this k-means method, first we design codebook with two code vectors, R0 and R1. We are assuming that the initial code vectors are R0 and R1. Now using these two code vectors R1 and R2, all the training vectors are divided into two clusters, namely C0 and C1. So using this R0 and R1, you are dividing your training vectors into two groups or clusters called as C0 and C1. Now for each of the two clusters C0 and C1, a code book is designed with two code vectors R00 and R01 for cluster C0 and R10 and R11 code vectors for the cluster C1. So again you are computing two code vectors. You are computing two code vectors for the cluster C0, that is R00 and R01, and for the cluster C1 the code vectors are R10 and R11. So again your clusters are divided into two clusters. C0 is divided into two clusters and C1 is divided into two clusters using these two vectors, code vectors for that particular cluster. Now this process is continued until the total number of code vectors is equals to L that we have assumed initially. Now when the algorithm will be stopped when the number of code vectors is equals to L that we have assumed initially at the starting of the algorithm. So by using this method, the search complexity is decreased over full search. Why? Because we do not compute the distortion between input vector X and all the code vectors present in the code book. So consider this figure. It is example of tree-structured vector quantizer. Suppose we want to quantize a vector X. That is the input vector is X that we want to quantize. So at each level I, consider this level as I. So at each level I of the tree code book, distortion measure is computed for the code vectors R I0 and R I1. Consider this as R I0 and this as R I1. Okay, here I is equals to 0. So R00 and R01. So here distortion measure is computed for the code vectors Ri0 and Ri1 if distortion between input vector X and Ri0, this particular case, and the distortion between input vector X and Ri1 is less than, if the distortion between X and Ri0 is less than distortion between input vector X and Ri1, then bit 0 is sent because as a part of the code word for the input vector X. Why? Because you are selecting the left subtree, right? Next, at the level I plus 1, consider this level as I plus 1. The distortion measure is computed for the input vector X with the two descendants of Ri0. Here the two descendants will be this one, R000 and R001 for the code vector R00. So if the distortion between X and Ri00 is less than distortion between X and Ri01, then you are selecting, this is the condition, then you are selecting left subtree of the this tree, left subtree. So 0 will be sent as a part of the code word for the input vector X. If suppose this condition is not true, then 1 is sent, okay, as a part of the code word. So take an example. Suppose the input vector is X that you want to quantize. So first, for the code vector X, the distortion is measured with the two code vectors here. Consider this level. So the distortion is measured with the two code vectors R0 and R1. If distortion between X and R0 is less than distortion between X and R1, then you are selecting left subtree. So 0 is sent as a part of the code word. Now at the next level, here consider this level because you have selected left subtree. So at the next level, the distortion is measured for X with the two code vectors R00 and R01 because we have selected R0 at the first level. Now if the distortion between this X and R00 is less than distortion between X and R01, then you are selecting left subtree. So 0 will be sent as a part of the code word for the input vector X. Now consider next level. Here The distortion is measured for X with the two code vectors R000 and R001 because we have selected R00 at the second level. Now, if the distortion between X and R000 is less than the distortion between X and R001, if this condition is satisfied, then you are selecting left subtree, so 0 will be sent as a part of the code word. Now this condition is not true. If this condition is not true, then instead of 0, 1 will be sent as a part of the code word. So for the first level, the code word was 0. For the second level, the code word was 0, and for this level, last level, the code word is 000. So using this code word, the decoder will generate the reconstructed vector. So here search complexity is reduced because we are not computing the distortion for all the code vectors. As you can see, this part of the tree is skipped. You are not computing the distortion for all these vectors, right? So this method stores twice number of code vectors as compared to full search case because the tree codebook is complete binary tree. Here you require twice number of code vectors as compared to full search. So storage requirement will be larger here as compared to full search case. The advantage of this method is that we only need to perform 2 into log m comparisons instead of m comparisons. In full search method you require m comparisons, but in this method, binary search clustering or a tree structured vector quantizer, you require 2 into log m comparisons. Now this extension an extension of binary search method is tree search quantization, in which trees are not limited to binary trees. If trees are not limited to binary tree, then this method is called as tree search vector quantization. Now the disadvantage of the tree structured method is that we might not get reconstruction point or vector that is closest to the input vector, so distortion will be higher. So as compared to full search quantizer, the distortion will be little higher in this tree structured quantizer. So I hope you understood. In next video we will discuss the design of tree structured vector quantizers, and we will also discuss what is pruned tree search vector quantizers. So that's it for now. Thank you.